wait, oh, that's not my question.
Yes, only for a slightly shorter time than I know Scott. But I met her as a postdoc, and when she was a graduate student, working with Jerry Spanier, and Jerry started working with us here at the Pipe and Laser Institute. Carole is a tried and true mathematician. She got her undergraduate at Berkeley in math and statistics. Is that right? Or
No,
just math.
They actually had an applied math.
An applied math. And then we went to industry, right?
Not UCLA.
Right away?
Yeah.
Okay. You went to UCLA, math and statistics.
Yeah.
Yes, okay. I knew there was math and statistics. And then you went into industry, worked a little bit at GPL and at TOW. And then she felt the urge to come back to academics, and that came to, at that time, Claremont Graduate School. I remember. It came Claremont Graduate University. There she met Jerry and started working on Monte Carlo methods, and through that association and with a little work with me and Bruce, developed some perturbation and differential Monte Carlo tools that are still used. And so she will share some of the work that we've been doing together and to extend beyond the fundamentals of what we just learned earlier this morning. So let's welcome Carole.
So yeah, I'll just be talking more about some extensions of the Monte Carlo methods and applications. Some will be overlap with Scott's talk, which is always good to hear things again in a maybe different way. So I'll go over some of the traditional Monte Carlo concepts and how the probability model derivation is done. The integral form of the RTE, we'll go over that, go over perturbation and differential Monte Carlo. And then I'll show how the spatial frequency domain and temporal frequency domain, FDPM estimators are derived. And then at the end, I'll show you how to run a simulation. If you're so inclined, we have software and all the different input that you have available to you. So I have this little roadmap. We have this integral differential RTE, which describes the radiance as a function of position and omega. They're bolded because they're vectors. And there's this method of characteristics that is used to transform it into, if you've taken PDEs, this is a method that they teach you, into the integral RTE, which describes the collision density. The symbol is psi. And then I'll show that from this, we derive a probability model or a random variable estimator. That with a detector function, because here we're getting a solution everywhere. We need to integrate that solution over a certain area in order to evaluate a measurement. And how we ensure that the random variable solves the RTE is that it is comprised of elements of the RTE. And defining the photon propagation in terms of elements of the RTE ensures that it's going to solve it. So we've all seen this equation many times. This is a time-independent equation. You guys have all heard what these are all these terms are. One of the reasons, why don't we just solve this? One of the reasons that Jerry, this is done in his book, transformed to the integral form of the RTE because he can show existence and uniqueness of the solution. That's a big thing. And then he can also represent the solution as a convergent infinite series. That's also a big thing too. So that gives you motivation as why this transformation to the integral form was done. So we use this method of characteristics. So if you guys took a partial differential equations course, these curves or lines are where you have two variables, independent variables of the PDE, and you parameterize them such that one variable is constant along those characteristics, then you can reduce the equation to something that is solvable. So Bell and Gladstone actually lays this out pretty nicely. They don't skip steps and they lay out all the equations so you can follow along. And you end up getting this integral form of the estimator. We have a psi, which is the collision density. It's related to the radiance by a factor mu t. You have on the right-hand side this integral operator. I call it fancy K because it's an operator. And then operating on psi plus s. And this K, fancy K, is actually the integral of this plane K, and the K has these, you saw these earlier, the collision kernel and the transport kernel. So this collision kernel includes the probability of scattering, so mu A plus mu S equals mu T, so this is a value less than 1, less than or equal to 1, and then the probability of absorption is mu A over mu T. So you roll the dice and you figure out, did I get absorbed? If I didn't get absorbed, then I get to scatter, and we use the phase function to determine which direction to scatter into. And then this is the T portion of K, where this tells you how far you scatter. And this is given in its more general form. Like Scott said, it allows for T to vary along this path. In a homogeneous situation, this reduces to mu t e to the minus mu t distance traveled, and very easily to integrate it and create a probability density function from it, and from that a cumulative density function, and then you can sample a random number, go into the cumulative density function, look down, that's the distance I traveled. So, and just to finish off, so S, part of the integral form of the RTE, S is taking the Q and transporting it to its first collision. So this is the density of first collisions. So you start with your source Q, you come in and you transport to the first density of, you use S to get to this first collision point. At this first collision point, you could get absorbed. You're gonna hit that C, which has that probability of mu S over mu T. Well, maybe you didn't pass and you get absorbed and use this little squiggle line that you got absorbed by the tissue here. If you didn't get absorbed, then you use that P function to determine how you change from omega prime to omega. And then you continue on. So you're just going through these density functions, calling a random number generator to say, give me a number between 0 and 1. I'm going to figure out from these density functions, create a cumulative density function, sample in there. Aha, I'm deflecting this angle, or I'm going this distance, t, and yeah, and so these S, C, and T are elements of the random walk. So I mentioned earlier that one of the nice things about the integral RTE is that the solution is a convergent infinite series. So if you bring all the terms, this is just the integral form that I had on previous chart, just brought all the terms over to the right-hand side. And if you remember from series, if you had, just to keep it simple, if you had 1 over the quantity 1 minus x, you could write that as 1 plus x squared plus x cubed, provided that the absolute value of x is less than 1. So same kind of concept here, except for we have an operator. And we're going to expand this portion of it into this series, and then we have the S term out here. So what that means is, if you were to multiply things out, the solution in a position R, direction omega, consists of the first term, S times I here, are those, so say you're at this position in this direction, that's where you want the solution, then things that came from the source, it'd have to be right here, like in a transmission situation. You come from the source and you transport it right into what you're trying to find, psi at R and omega. The second term here is all possibilities of coming from this source, then colliding once and then going in. So you definitely have to collide once if you're in a reflectance geometry. And so on. So these are the contributions of the photons that have collided twice. And if you were to sum this all up, an infinite, for all the different numbers of collisions to infinity, you would get this solution, and it's a convergent series. So that's a nice aspect of the integral form. But we're just talking now about, we have, radiance as a function of r and omega, or collision density as a function of r omega, but we really want to make a measurement. We need to integrate that global solution, if you will, with some detector function to give you an estimate of measurement. So let's just think about reflectance. So say we have a detector on the surface here, and the detector function that we could use is this function f. Basically, this chi function is saying yes if it's value 1, if it's in the spatial extent of the detector, and if it's within the NA of the detector, and 0 if not. So, photons may come out the surface away from the surface region of the detector, they're not tallied, or they could come in at a more oblique angle, they're not going to get tallied. So this detector is just picking off those photons that are coming in within the definition that you are trying to mimic in some maybe experimental, maybe you have a fiber here, a certain extent with a certain NA, and you're trying to match up your Monte Carlo results with that measurement. So you would define these aspects of your detector function. So now so that's kind of like the analytic world. Now we're going to go into the probability world. And the probability world is composed of creating a random variable that defines the method of tallying. So we define this C is the random variable, in terms of the elements of the RTE, like S and K being C and T, and a detector function, and sometimes potential weights. You'll see how that works. And what you end up doing is evaluating this random variable with a measure. Okay, I kind of have to say, when I first learned about this, measure kind of made me freeze, like, oh my gosh, I don't know much about that. But just think of the fact that this measure arises from the probability density functions that compose S and K. So it's just those mu S over mu T, the Henry Greenstein probability of scattering. You have that UTE to the minus mu T distance. Just those things are the PDFs, probability density functions, give rise to the way that you're evaluating this random variable. Okay, so then you launch n photons, sum up these random variables and divide by the number launched. That gives you an estimate of your measurement. So let's look at the estimator for reflectance. I've kind of reduced nomenclature here, just calling P1, R1, and omega 1, meaning it's the location and direction at this point right here. P2 is here, P2, just to keep things simple. One of the things you have with detection at the surface is that this transport from this P3 actually went beyond. It actually went beyond this point, but it got interrupted here because we're at the boundary, and so we put a pseudo collision there. So just little details you have to keep track of because this path length is from this P3 to that pseudo collision. So we have this modified terminal estimator that allows us to determine reflectance. Looks kind of crazy. In the numerator are those elements of the analytic solution, S, and that's why I call it SRTE, KRTE. Okay, and then here's our detector function here, that's that chi function. And in the denominator here are elements of the way that you ran the random walk, and I'll get to that in a second, because they will, if they're different from the numerator, they will invoke weights here. So, okay, I think I covered all that. So I wanted to describe a little bit of a random walk process. I kind of edited some of these charts because of questions last year. So this random walk, so everything with a sub m is the random walk process. Okay, so in that random walk, just like the analytic solution, we have how photons are initiated to their first density, how photons move from collision to collision, so that K involves C and T, and then how they terminate, so that right to that pseudo collision. And this measure, or density functions, that they arise from the elements of RTE. So there's like this equivalence between the analytic situation and the probabilistic. But the fact that we define the random walk process and the estimator in a certain way ensures that what we end up evaluating after running a Monte Carlo simulation does indeed solve the RTE and provide what we call an unbiased estimate. So let's keep things simple. Analog, so Scott mentioned analog. Analog was the very first random walk process because it's kind of physical. It's kind of like, you just move a photon around, and maybe it gets absorbed, goes away. Then you start another photon, moves around. And in the way that the people who developed this is that, I think I lost juice. Maybe I'll just walk over here. So the measures, or the way that you run the random walks, is exactly like what's in the analytic function. This means that the transport is done using that ut, e minus ut distance. So it has a mean free. You evaluate that and get determine you can use that to evaluate the mean free path, the average of sampling that density function. That's 1 over mu t. And that kind of crazy estimator, oh gosh, a lot of things, they just all cancel. They all cancel. It ends up being a binomial estimator. One if, come up. One if it, thank you so much, Richard. One if it exits the detector and 0 otherwise. So in this case, the photon weight stays 1, and maybe it gets absorbed, or maybe it keeps on going. This one was fortunate because it went out the detector, but there's going to be, I probably should have shown ones that came out here. That didn't make it up, and that's how this analog random walk process is done. So because the photons are getting absorbed, you could imagine that something very far from the source will never get detected. So a different random walk process called discrete absorption weighting is done. It's an alternate method to account for absorption. So instead of letting the photon get absorbed, so no absorption, we account for that change. We're changing the random walk. You can't change the random walk and not alter the weight of the photon. It's a balance, and otherwise you won't solve the RTE. So we define the way the random walk is performed by this SM and KM. And basically what Scott was describing is done here, where you start with a weight 1, you go to your first collision. At that point, your weight changes by mu s over mu t. It could be, I put full generality here, so this could be very heterogeneous. The optical properties at this point could be different from this point, but let's consider homogeneous. Then they're all being deweighted at each collision by mu s over mu t, such that before getting detected, the weight would be mu s over mu t to the power k, k being the number of collisions prior to detection. Another way to do this is using continuous absorption weighting. I really liked how Scott described how okay, now we're just going to scatter with respect to mu s. And what that means is that that transport kernel is now mu s e to the minus mu s distance traveled. So, so this is how the definition of the random walk equations are. And lots of cancellations, you end up, if, let's just do homogeneous, you end up with pretty much Beer's law here, e to the minus mu l a l, l being the total distance the photon traveled, and then 0 if it didn't make it out the detector. It's always got this detector function saying yay or nay whether we're including it in our tally. So let me show you the, let's see if this commits not, oh, here it goes. Okay, so analog, discrete, continuous. Here's one photon. I'm also showing time, because that's a key way of separating how these guys roll. So this is one photon, that's where it got absorbed. And here you're seeing how the photon's weight is being decayed on each collision prior to exiting. You see, I used the same random number seed for these simulations. So this CAW is slightly kind of a bigger expanded form of this DAW because we're using 1 over mu s, which is longer than 1 over mu t, to determine the interaction distances. Okay, so let's roll this farther. So now at let's see, that's 100,000. I'll just talk about this. You can see now that the difference in timing here. It took 0.7 seconds to run this many photons, where it took 8 or 9 seconds to run this many photons for these methods. So that's kind of a comparative factor in using the different methods.
Why did it take longer?
Why did it take longer for CW?
Yeah, for like discrete versus analog, because it seems like it's just one extra multiplication each time.
Well, because of the fact that so these guys are running photons since absorption's not being allowed, they're running photons all the way until they exit phase space or top of the tissue or whatever domain. Whereas these guys are actually getting absorbed into the tissue. Once they get absorbed, we roll to the next photon.
Got it.
So, yeah, so that time differential, I mean, I'll kind of have a pros and cons after.
Yeah, so you don't see that the analog is much noisier than the discrete.
It is.
It's a little bit more pixelated, but.
Yes, for sure.
Carole, can you just go back a couple, like when you're like 100 or 1,000, because I think that gives them a more intuitive feel for kind of how you're filling the volume. So go to 10.
Oops.
Sorry. Go to 10. Just step through that a little more slowly.
Just go to the end of your talk.
Okay, let's see. The controls on this are kind of funny.
Sorry. Yeah, stop.
Here?
Oh.
Where'd you stick to?
Sorry. I always.
Me screenshot.
Stop. Okay. Okay.
I did go to a million, but, okay, let me see if I can just.
It's okay, don't worry, we can
Oh, yeah,
try to do it another time.
sorry. But let me finish it because, wait, this is, hold on, okay, I'm at a different place now. Okay, this mu s prime over mu a is 10. Okay, just to give you an idea. We looked at that on Tuesday. So I'll let this roll. And then what I do is I add in a detector and I create what we call photon bananas. Gives you an idea of the sampling region volume that photons that necessarily detected experienced. So, yeah, sorry, wasn't trying to type here. Okay, so let me go to, this is higher absorption, US prime over mu a of 1, higher absorption. Now you can really see how noisy analog is. Okay. Oops. Okay, so kind of a little quick sheet on why would you use one over the other? So analog runs very fast, but tallies far from the source can be difficult. Okay, I threw this in just because it's me. We always proved things using analog. Analog matches the RTE closest, so it's the easiest thing to use to prove things when I was working on my dissertation. DAW, tallies far from the source, are possible. No path length information is needed, only the collision, weight changes only at the collision. But the only way for the photon to stop its random walk is to exit the domain. So there's an increase to computational cost there. CAW tallies far from the source. It can tally in thin layers too, better than DAW, because you're going to go through a layer, you're going to have a path length in there, but possibly you might not scatter very much with DAW. And you can use Beer's law to account for various UAs if the path lengths are solved. Again, you have to wait for the photon to exit before you start a new photon. But the downside of CAW that I have found is that if you're trying to, say you have a completely voxelized tissue, and maybe the optical properties are changing with, pretty regularly across the voxels, then you have to be able to determine little partial path lengths in each voxel. That can increase your computational cost as far as code figuring out, okay, I entered, went through this voxel, that's kind of easy, oh no, but I entered and had a partial track, that sort of thing. Any questions so far? Because I'm going to change topics. So I'm going to go over perturbation Monte Carlo. Perturbation Monte Carlo is used to determine the change to the measurement. I notate it by I hat. Given the fact that the optical properties in some subregion or the whole tissue have changed. And I do it for a simple, like there's homogeneous and then there's an area that has changed optical properties, but it could be very heterogeneous and then you change the optical properties in a certain region or the whole thing. So one of the benefits of perturbation Monte Carlo is that you use, well, let me flip it. One way to solve this problem is that you could run another simulation that had a two-region process in which you enter this region, change to these optical properties, move around in this region with those optical properties, come out and use these optical properties out here. However, the bad side of that or downside of that is that you're running another simulation, could be computational costly. If you want to know a lot of delta alphas, alpha being the optical properties, you're just curious, like, how much does this actually have to change in order for me to see a change in my signal? So that's kind of a common question that arises. So the benefit is that PMC uses the original set of random walks, just keeping track of pertinent information that's happening in here, and can determine the change to the measurement based on the change to the optical.
Carol, there's a question back there.
Oh,
Sorry,
yes,
sir.
John.
I need a practical translation of what you just said. So when you're talking about change, for a practical application, is it you're modeling the dermis, there's a blood vessel underneath, and because you entered and exited the blood vessel, the properties change? Or you can also use it that there's blood flowing in the blood vessel, and there's a time dependence on the blood flow.
Well, there is a way to, I mean, this can be used to provide sensitivity results, meaning that you want to see the fact that maybe you don't really know, maybe that blood is changing in optical properties, and you want to say, okay, if the blood optical mu A is changing by this factor, what is the change to my measured signal? That sort of thing.
Oh, okay.
Yeah. But there's no time dependency.
Yeah.
I mean, you could use it but this method is based on the fact that you have these static optical properties.
So Jason, you
Stationary.
just want to run a virtual experiment. If I have a certain source configuration and a certain detector configuration, I'm interested in saying, am I sensitive to potential cancerous changes at the dermal epidermal junction? Okay, and that's going to change my absorption or scattering in a particular way. Instead of running two separate Monte Carlo simulations, you do the one without the cancer, and then you do it with the cancer to see what is the change in my detection.
Okay.
And then you can look at it for other detectors. So it's kind of a quick sandbox to say, how sensitive am I to a change in the
Yeah.
physiology?
So the translation in my head is it's actually like a virtual slider,
In
a
some
virtual
sense.
variable slider.
Yeah.
Yeah,
Yeah. Okay.
yeah, you could see that. So how do we do this? And the thought process in a practical way was that maybe you have healthy tissue, and then you have some progression of disease that's happening, and that's going to change the optical properties. And we want to know, how is that going to change the measurement? So like maybe in this tumors region here, we run a random walk process and store the path lengths in here and the number of collisions into a database. And then from this, I'm going to say that this method can work for reflectance, fluence, radiance. Once you store this, you can post-process it, and I'll show you that. So now you have this delta optical properties. The way that we are enabled to determine this I hat, the change to the measurement, as we apply something called the radon nicotine derivative to the estimator. And I put a hat on that because this is now the estimate of the perturbed system, the system where you have this change in optical properties here. And these ratios are just those probability density functions that are using the perturbed optical properties. So instead of mu t e to the minus mu t for distances, you have mu t hat based on the change here. And it allows us to weight the photons appropriately using the random walks based on the background and provide an estimate of the change to the measurement. So let's do discrete absorption weighting. We're going to assume it's homogeneous, and we have the weights. As I showed before, it's got this mu s over mu t to the power k, k being the number of collisions prior to detection. I put a factor here that counts for specular of the source coming from air to the tissue some photons get specularly reflected. And then we save the path lengths and collisions in here. So let's take a real example where we're changing mu a and mu s by delta mu a and delta mu s here. You can see that this is the base weight. Now we have a ratio, so this is pretty much the C, but using the perturbed values divided by the non-perturbed values. This I just simplified, but this is mu g either minus mu g distance traveled, and this is the total path length in this region, perturbed region. This is J is the number of collisions in this perturbed region, and you can get an estimate of your reflectance. So I show here the baseline in red. I show changing mu a by a factor of 1/2, and then doubling it. You can see there's correlation going on here and all. That's actually working to your benefit. I'll describe that in a bit. So one of the nice things about PMC is it leads to differential Monte Carlo. Okay, differential Monte Carlo, that's great, because now we can get sensitivity coefficients. We can use this now, we can use Monte Carlo in a gradient-based optimization, because now you're just processing based on reading a database rather than running a complete simulation in each step of that optimization. And that the way we find an estimate of the derivative is that we take a derivative of the estimate. And this was a big portion of my thesis to prove that. So you just take this was the equation that was on the previous page. You just take the derivative with respect to delta mu a and delta mu s, straightforward, nothing crazy going on here. And that gives you estimates of the derivative, which you can tally after you've saved that database. So this shows you a plot of the derivatives. So the advantage is that you can get all these results based on one simulation. That's good. Okay, this correlation is actually working to your benefit because this difference is capturing the difference due to that optical property change. And if you were to run an independent simulation, then the statistics of that change, because you ran an independent simulation, are also included in the differences here. So, and it runs fast. So I ran 1 million, it took about 1,600 seconds, but to post-process takes about 2.5 seconds. And I'll show you how it can be used in a gradient-based optimization in another lecture next week. So I'll show you how the spatial frequency domain reflectance estimator is derived. Is anyone doing SFDI here? Yay! And Bernard. Okay, so you guys are very familiar that you illuminate the tissue with these sinusoidal patterns. This didn't really match what's shown here, but you get the idea. There's these sinusoidal patterns. And what is measured, reflected out, is decayed in amplitude and also shifted in phase. And those differences allow you to obtain information about the tissue subsurface characteristics. So this little roadmap that I showed before, it just gets a little twist. So we take the radiance, we Fourier transform it across transverse, meaning x and y, Fourier transform it, and then we do the same thing. We do the method of characteristics, get the collision density, and then we get an estimate. I put hats here because we're in Fourier space here. Okay, so same sort of thing going on here, except for we're working on the Fourier transform equation. So we start with the time-independent RTE, then we 2D Fourier transform over x and y. Difference here, this omega used to be a vector, now it's omega z here. These all have independent variable of z now. And then this red term here is a big difference. Where this L hat looks like this. So yeah, this is the big difference. And Adam Gardner, who was a graduate student in Fossum's lab, came up with this derivation. It's kind of a shortcut. I should say that, prior to having this way to determine spatial frequency, you could get spatially resolved results and discrete Fourier transform them. That has problems. It has aliasing, problems with discretization. So this was a nice solution to get without having to do that, and because we're working in Fourier space. So yeah, it's similar to transforming the integral differential RT to the integral using the method of characteristics. We have an integrating factor, right? Scott talked about, similar to the method of solving ODEs. And we end up getting, everything's hatted, we're in Fourier space. We have a K and S now with these red terms. Okay, so now, what do we do with our estimator? I'm going to use analog because whenever I prove something, analog is the best thing to do. So when I have those functions that I showed on the previous page, substitute these in, cancel, 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 you end up getting something that you tally e to the minus 2 pi I spatial frequency, fx is spatial frequency, and this distance is the distance the photon emerged relative to the position it entered. So you're putting in a point source here, and this is, I should have said this is just for sinusoids along the x-axis, like the picture I showed. So you're putting in a point source, you let the photon move around, it comes out over here, you figure out what's the x-axis distance, and that's what you tally here. And you can apply any set of spatial frequencies that you're interested in here. So that's how the spatial frequency domain estimator works. Oh, sure.
So if I graph out xk, that last term,
This one?
yeah,
Uh-huh.
will I be able to figure out if there's a subsurface structure inversely, or is it just gonna give me random noise?
Well, so this
Where
is,
the photons quenched or
so
absorbed?
this is just for one photon. In order to estimate the
All of them.
you have to run a whole bunch.
Uh-huh.
Okay, and then I should also have, just practical, this is a complex estimator here, got an I in here. I actually tally the real and imaginary parts and tally them separately, create a mean, and then from that, I get an overall, I can have an overall mean, real and imaginary, which I can determine amplitude from, just using the amplitude, square root of, and then I can also get phase from. So.
Oh, okay, I'm sorry, it doesn't work because you're in Fourier space, never mind.
Okay.
Okay.
Okay, well. So, similar kind of thing works for temporal frequency domain, or F, a lot of times we call this FDPM, frequency domain photon migration. You put in a sinusoidally amplituded modulated source, and then you measure at a detector what the decay to that amplitude and the phase shift, and it gives you ideas about what's going on below the surface. So same thing here. We take the Fourier transform of the time-dependent RTE, and then we use method of characteristics, get collision density, and an estimator. So let's see. So here's the time-dependent RTE, the temporal Fourier transform of this. now we have this little omega. So this is, big omega is the direction, little omega is the temporal frequency. And so this term, new term in red, is part of the equations. And Testorf did this back in 99, another shortcut method. So we use the method of characteristics, same as before. We get this equation in Fourier space. Your K and S have those different red terms in them. So what ends up happening if you substitute it into the estimator is that what you tally is when the photon exits, you tally e to the minus 2 pi I temporal frequency time that it exits. And in Monte Carlo, the way you determine time is you take the path length, you divide it by the speed of light divided by refractive index mismatch, and that gives you time. So that's how the FDPM estimator runs. Any questions? Because I'm going to shift now. I'll keep on because maybe you'll have the group thing. So I wanted to describe a little bit of our software. We have what I call the conventional Monte Carlo because we have an unconventional Monte Carlo too. So this is part of a library we call the VTS. And there's ways to interface with this library, kind of based on how far in you want to get. We have a panel on the GUI that you've been using. If you just want to point and click and run a simulation, we have MATLAB interop. Everyone's used to MATLAB, and we have commands that can interact with it. Or if you really want to run the full capabilities, then we have a command line. And the labs this afternoon will have examples of all 3 ways to interface. So it's really easy. We have on our website, you can go to developers, go to the GitHub site and downloads, and it has the downloads for the GUI, the MATLAB interop, and the MCCL. We have lots of sample-in files, and then lots of documentation on the right-hand side about how to set up an in file, how to run a simulation. I wanted to go over some of the sources that are available. Jonica wrote the code for the sources, and he and David Kucha got together, I think, and tried to figure out every possible source, optical source that somebody might want. So the sources include points, lines, circles, ellipses, rectangles. You can put in a bitmap image. They can be flat, or they can be Gaussian decay. Inside, we have diverging, angled, diverging, and then angled. We have converging. We have a fiber that has different efficiencies on the sides versus the bottom. We have, say you have a source inside that's emanating light from the surface. We have a sphere, ellipsoid, cuboidals, and then maybe it's emanating throughout the whole volume. That's what this is supposed to represent. And there's on the right-hand panel, there's a source definitions link that shows the definitions of all the sources and all the different things that you can define as far as angling it, converging it, diverging it, that sort of thing. Yes?
I have a question about the top view, the light source. Can I bring my design for the light source?
Can you bring the what?
My design of the light source, how it's look like. For example, like cross shape of the light source. Can I put it there?
If you have a cross shape of the light source?
Yes.
Yeah, so you mean like 2 lines
Yeah.
like that? Well, we don't have a cross. However, RTE is linear and you can use superposition. So you could run a simulation with this source. You could run a simulation with this source and add the results.
Yeah. That was just because usually in practical way, like the light source usually horizontal, vertical, diverging angle is different. So that's why I just want to know.
You mean this angle here?
No, like if you use the LED light source normally, when you look at the LED, the horizontal diverging emission angle and vertical emission angle is different.
I see. Um, Yeah, because the way that these are defined, good to know, maybe we
Yeah,
need
this
to
good
add,
to know,
maybe we
but-
need to add a source. Because the way these are, it's spatially uniform within that solid angle here, and then you can rotate. But you're saying that it's stronger along one axis than the other. Yeah. Yeah, we don't have that. Could we have that? We can't add that. Why can't we add that, John?
I had a question.
We can discuss offline.
Okay, we can discuss.
How would your software compare to other ones like the MC MATLAB or
Oh, ZMAX. Okay, ZMAX is Monte Carlo is pretty fundamental.
Okay.
I'm not sure about, I'm familiar with MCML. You called it MCMAP. Not familiar with that. Is it actually written by MATLAB?
I
MathWorks?
don't
No.
believe so.
Okay.
Are you referring to MCX by Chin Fang?
Oh, MCX?
I believe it's called MC MATLAB.
That's MCMATLAB. Yeah, see, it's on the MathWorks. But it's part of the file exchange, somebody
Yeah,
uploaded and made available to
that's what
everybody.
I
Is it?
was
Okay,
trying
well
to
then,
use,
yeah. Yeah,
Okay.
I'm sure, just depends on, one of the things that I have found is if you're running Monte Carlo in MATLAB, you have the overhead of MATLAB. Whereas, if you put our code onto a Linux computer, run a command line, it's gonna run lickety-split, so.
Okay.
Yeah. We have tissues that can be layers. You can embed a sphere, ellipsoid, cuboidal, cylinder. Works well with blood vessels into the page. You can put multiple. We have concentric cylinders because that seems to be a tissue type 2 that people are interested in. And then detectors. I kind of want to go over this because we use cylindrical and Cartesian coordinate detectors. So from a top view, like if you're getting reflectance versus row, as we call it, source detector separation, we're actually capturing photons out these different rings. It allows you, if you have cylindrical symmetry in the problem, like just layers, then it's a more efficient way to collect photons because you get them all out this big region rather than just a little circle right here. And then you divide by the surface area of that region, you get a per square millimeter result. Then we have regular Cartesian. Here's what the inside of a cylindrical. One of the things that has come up in the labs I thought I'd describe. So here's a Cartesian voxelized inside of the tissue. Forgive my perspective here. But inside, say we're interested in radiance. So this is a function of position, theta, and phi. So position is clear on this grid. But in every voxel here, positive z is going into the tissue, which means theta ticks off from there. So theta is 0 going down, goes to pi over 2 here, and pi over 2 to pi here. That's the way theta is. Phi is going around here. So let's just keep it simple, and let's say we were interested in radiance with this theta beam. Then it would be capturing, while you're sitting in that voxel, it would be capturing all the photons that are going down in that downward motion. Whereas in this theta bin, it's capturing all the photons going up. So it's going to come up in the lab. Very easy to run. We have it on Windows, Linux, and Mac OS. You describe how you can run it, and then we have a script in MATLAB to to plot the results. I just give the units here. These units are used throughout our software, which means the GUI. So time domain is in nanoseconds, temporal frequency gigahertz. A lot of times people use our GUI and plot something, and I don't see anything like I used to see. And it's because maybe they use different units in their input. Okay, so I said that we have conventional Monte Carlo and some unconventional. We have scaled Monte Carlo in our GUI. And I want to differentiate the two because scaled Monte Carlo takes a simulation for reflectance based on row and time, and then they save these. This is something Keenly and Patterson did. They save the reflectance results, and then they scale it. So based on, it's kind of like you have this domain, and then you change mu A and mu S, and it kind of changes it. So like if you were looking at a certain row with these optical properties, well, it would be a different row if you change these optical properties. So it's a scaling. And somebody in a group in VP, Michele Martinelli, and some of the other of us that were around then, we took Keenly and Patterson's and saw that they really needed more adaptive binning in the far time and far row. And we also applied a non-uniform rational beam spline. And that's also in the GUI. So when you pull down the forward solver panel, you can see the basic or the nerves. And the reason why I differentiate, these do not provide estimates on a photon by photon basis. They scale a result. But it's nice, they provide quick and dirty results that maybe, just hypothetical, you have a question in your mind, what would happen? And you can just plug it in and see, okay, I kind of have an idea. Or maybe you just want to compare two things qualitatively, see how. So hopefully I've covered, this roadmap of getting the interval form and how it was used to get spatial and temporal frequency results, went over perturbation differential, and how you could run a simulation if you were so inclined to. So thanks.
Questions for Carole?
Are you guys going to go in groups, or we're just going to do it? Let's just do it.
Well, since they have no questions, it looks like they need to generate questions as opposed to last. So yes, they go into groups maybe? Yeah? Okay.
Did that work for you guys? Oh,
Yeah, I think so, yeah. Okay, so groups of 4 or so, and give you guys 5 minutes. Generate questions.
I'm looking forward to playing your video.
We're gonna cup of coffee.
The perturbation, so if you
Not questions.
have,
Maybe it might be like exactly what I need.
Overwhelmed?
Don't you?
Well, I guess after the lava we'll get more interested.
Yeah.
Yes. They have a lot of examples.
I guess
So maybe I should.
So
How do you want to?
for you to set it outside and see how many.
You know what I mean? So I know for that, it's.
Their way seems like it was.
But he's not.
He just told me about it a minute ago, that's what I thought I'd ask.
So you have one ability.
Maybe, I don't know. That's like maybe.
Is it because you're visualizing?
Because it's a note.
You think that
What
you
we can do, like, that's why I'm curious, like,
What is it?
divergence?
No, I love the run.
Yeah, I would think that.
My understanding of the lecture is perturbation and then
Actually, like when I did
The way I
just,
Oh, so maybe they're square.
software. Looks like when you're doing
Oh, so it's not MC map.
Like, it's
Oh,
okay.
yeah, they have like software, they have like
But it's probably rectangular.
before you get.
That's fair. Yes.
Why do you want to use a prompt?
It might be no big deal.
Yeah, they might not.
The students get smarter and smarter.
Because
They're not paying attention.
Because integrals are key.
Why do you want to do a prompt?
They pass it down, or they come out going.
Why do you want to do a prompt?
And then that's when you
I learned like math on the street.
best way to make
random stuff.
points.
But it's not true for us. We have the RT point that, point away. And then we
Whether they-
and apply the RT again. And again,
The big university,
that is what I got out of it. No, I spent 20 minutes with Dr. Troy, like walking through, but that was the part that I got off.
What was it doing?
I'm taking another paper where I didn't really look at what CAW was. Oh, discrete absorption rate and
Based on but basically, I did the arrays.
the continuously changing.
Yeah. The first one they consider and then come to
That's what I'm saying.
And that is that true force by Dr.
All
that you would calculate just the scattering weight, and then you get it, and then you
how can you very much until you get every time.
And at that point, you also need to realize they were doing is also there is a.
So they're using,
And then also they were doing.
my philosophical is like,
Direction.
got to the frequency by adding frequency.
Nature takes over.
Scattering. Why are those?
Very fine.
well, it's really, that's where how they prove
So we always validate our code
because MATLAB itself
those solutions are
Now the line just right interrupting with the fish, and that's
We're not into
okay. You're learning the part of this like the information like the state of Massachusetts, right? Or any other useful information.
you're right.
Yeah, when we know the light is it's not like
You'll notice we don't
later
have
we will don't interact.
Oh, yeah.
I was serious. I'm looking forward to
trying out yourself.
And then now you can do,
Everyone doing different.
because from a business perspective,
No distance really, or you can do it as long as.
You can do for any.
I like writing on it. It feels good. It doesn't feel like that.
Wow, things get really dicey.
Those are, if you are passing those, then you want to like back.
Not necessarily. You can use for every. You just wouldn't. You can use for any source of vectors. Yeah, it's generalized. The problem is Monte Carlo is computationally expensive. So when you start following the one model, you want to use Monte Carlo just because it's computational. But you can. It's Monte Carlo is a general. Yeah, you can use it. Yeah, she had it there. She had it there on the slides. It was long source of vector separation. Like, I think we choose.
So looking back,
Running the simulation is.
do you feel like you're
right? Because I remember.
You're at the place
I don't
that you
actually.
So that's what she should do.
It's not as far as accomplishments, more just.
But like, I remember talking about the
No. That's why I thought.
Right now, are we gonna?
Always good to start out.
Yeah.
Yeah.
So how if you have multiple, like, and in that case,
So we can get it.
that's the part that I don't how to do it in an efficient manner, and that's the part. It's just that you can obviously the Monte Carlo
Is that why you use it?
for one part of the picture, and then once you enter the next picture, you would have to. Your step size will go on.
I got my signature.
And then if it goes into the next one, layer, you have to do it.
So then you
Once it re-enters, you have to change your style.
and then set them up.
That's why I don't know anything about speckle at all until like one next season.
You don't have to, actually, you will.
Yeah, you can now.
You look at the message, you're putting it in a, you look at the vibration and
I actually,
They were doing.
I had a, I
I
used to work for,
all the efforts is the
Random numbers from 0 to 1 divided by your.
Thomas and Alberta.
No, yes.
Anybody with like a become nice.
They've got a whole range.
That's why the.
I guess they probably have.
So, but the thing that is, though, is that the government had to install, basic server protections.
Yeah, we would.
You understood the part where.
Over there, yeah, I'm actually giving a lecture and.
Weird location.
Yeah, but.
So, and then because of the temperature, it
UA
gets really cold
Kathleen.
in Edmonton,
Yeah, that
right?
is, you know, that heat intensity. The ratio of intensity is proportional to the exponential of the path. And that's why you use this pattern to calculate by the.
I don't think that then makes.
And I was like, oh, this is a terrible way to have to work.
Yeah, so when we were.
What if,
collisions.
was at the Costco, there's like,
And then we have.
why are the little boxes in front of the parking?
Oh, okay, you landed there. By that way, right in the car.
I could tell that, yeah.
There's this price point.
Yes, you would like the concentration.
Yeah, it's an acquired case.
When are you done?
So, yes, you can get a concentration for that too, but one side of the minus UA and the path length. So we know the path length because that was our.
I remember we had to go Edmonton, and I was like, this is already terrible, and you want me to go towards Fort something like McMurray, right? I was like, no, I don't want This is already too far north for me.
Right, the equation, what was the equation? The level of
I know what this is
I started out.
Yeah, this one counter was
Further, only like a 300 guy, right?
That's the way that I write it.
There are ways to do the inversion, using correlation.
So we sent one team in February, and then nobody volunteered.
So absorption of the combination of
So then
coefficients and
I got
concentrations.
lucky, and the February team told me,
Multiple
do
different
not go
extensions.
July or August, it's July.
It comes from it comes from
But
the
I
fact that
remember
when you're
the
expressing UA and when you're expressing
But it was still,
what happens
totally we're not prepared to know.
based on got a 2.9 at the beginning. Yeah.
The differences and then update the next guess of where UA or then it runs the perturbation Monte Carlo, gets the new Monte
Here,
Carlo
you see,
result.
when you have concentration, you have absolute
on dictation. But their concentrations times your half point. But when you're using the physics method, you have the ratio of intensities is just the exponential of
I have estimates, just little details like, you can't turn off all the water.
But when we equal these two to each other,
Or else your pipe would gone.
you get
And this is just common sense.
It was good because it's
Until you're first,
and the
my
half point
first
fell off.
organized.
Yeah, it was,
Yeah, the MUA equals 2.86 extension
on
times.
the way home.
This is the round of things that I do every single day. This is what I do.
If it's
I
really
assume that
bad.
our optical properties are right. How do I go from optical properties? How do different examples interact? How we select a wavelength range if we're doing broadband with 600 nanometers off.
I see.
How do I pick?
I just said, I mean,
If you're,
but would be any way, that's how it's
Shine light on it, what happens in real time.
They don't write on it.
Like in the lab,
They don't. They laugh at you for doing
I
it.
feel like it's a lot of if you're not seeing it.
yeah, I have.
Either,
And there's so
it's
many.
funny, it's like, I do this all the time.
which ones were the?
The computers are great, but when
They just,
dimensionality of your system gets larger and larger.
I don't, because I
At
get
least I
shut.
had like a
So
better,
now
I
I
didn't even know.
Yeah, I mean, if you have a simple 1 or 2 layered system, yes, like.
try to be,
Like when I'm
it's hard if it's a really bad day.
Yeah, people have,
It's like, what is the difference between
sources and detectors. that are trying to
perturbation
solve
versus doing their method?
the only time that I prefer.
The solutions are always kind of blurry. Having more and more detectors.
The perturbation, it's earlier, it's before the different stuff.
Computer.
So it's actually
That way.
Yeah, what is?
I think, this is my,
Rats, they put little rats in, they image them.
Oh, it's from the year before.
a lot of times it's so.
Find them.
You never know.
Yeah.
Like a, hey, the light
That would
turns
be
green.
it. That would be it.
Okay, well.
Or the one who cut you off and you wanna go boom. So I think they should have.
The effect of
Like a button button.
light coming through here.
They put the slides online.
It's 2023.
Letters and that.
She'll like do that, and I'm like,
That's the perturbation.
I like that.
Yeah.
Thing first, it was a nice
I wasn't
little
like,
diagram.
any reactions?
I mean, a little bit of both.
Yeah.
It's not
Like, you just have it to.
because, you
Yeah,
know,
exactly.
coming in with all the.
Yeah, yeah.